haven't seen you in some years, I think.
I don't know. I'm still alive. Those are cinnamon sugar. They wrap them up. I don't know why. I guess so they don't.
So that we don't contaminate everything else.
Yeah.
Which one is regular bagel?
They are in that bag in the bottom.
Oh, do you want to have a regular bagel? Alexey? Alexey don't care. Okay.
I think you should write the stars.
What?
Not drink any coffee or eaten any bagel this morning.
I don't know. That's why I was trying to facilitate that for you. Is there other things that need to happen? Are you sending the link to your parents?
Yeah.
Will you send it to me too? Sorry, I was trying to not take too many of the seats close to the entrance.
I just don't want
Try
you
to-
to look at me being like, I have no idea what you're talking about.
I will go to my goal is sitting over here. Got the computer on the screen.
Yes, but.
Kind of.
And it also is on the side. Which is better, right plane or left plane? I think right plane. Okay.
Even made one of those things we did, we can 3D printed it. That guy is a number.
Yeah, I heard that's what you heard. So keep it easy.
Keep mine out. Usually sit where you want. Okay.
You send me the link.
Yeah. I don't think we've actually Peter, it's been a little while.
Yeah.
Okay. Looking forward to it. Yeah.
Rochester and least how much time can super optics there?
Yeah, I'm sure it's
I think we're still waiting for Doug.
I was a little worried about some of the construction because they dug a big trench across one of the roads I normally go on, and they have us go on a 2 or 3 road detour. And then the road to the Prospect Station parking garage basically shut down for a while yesterday with weather digging across it. So it's a 1-lane road, so I thought, what do I get down there? And I'm like, in the driveway at the Prospect Station garage waiting. But anyway, it worked out okay. Sometimes I FaceTime in from the driveway. I mean, there's a sign on the door. So.
Oh, there.
That one?
Right in front of the clean sheet. Yeah. You okay if we start?
Yeah, sure.
Can we turn off the lights that are like again that one? Yeah, that's perfect. Yeah, leave the third one on. Not that one. That one. Perfect. That's good. Yeah.
Okay, so thank you everyone for coming. Welcome. It's a pleasure to introduce David Mason. David has been working on our optomechanics experiments since at least very early in graduate school, about 5 years, and has seen this project from through a major rebuild, through an effort on quantum physics, and through, very much to our surprise, an effort on topological classical physics. So, welcome.
All right, thanks a lot. Thanks for coming. So today I'm going to talk about exceptional points. So very briefly, these are degeneracies in open systems, so systems that have loss or gain. But essentially, this is just physics that comes out of a careful analysis of harmonic oscillators in terms of complex eigenvalues. And so it turns out, well, what I'm going to talk about today is how we were able to study this physics using our optomechanical system. So I'll sort of briefly introduce optomechanics and review our experiment and some of what we've done with it. And then the second half, I'll move on to introduce exceptional points, starting with the toy model, and then talk about how we were able to implement this in our experiment, introduce some of our results, and finish with some more recent results, sort of extending this to a more broad class of systems. So, getting started with optomechanics. This is sort of the canonical picture everyone has in mind for optomechanics of a Fabry-Perot cavity with a movable end mirror. So one of the mirrors is harmonically bound, and this has two implications. First, the position of the mirror will set to change the frequency of the cavity. At the same time, there will be a radiation pressure force from the intercavity light on the mirror itself. And so this results in a sort of coupled system between these two variables, the mechanical motion and the intercavity light field. So since the mechanical motion changes the light, by monitoring the light, I can monitor the motion. So in that sense, I can measure my mechanics. At the same time, by controlling what light I apply, I can control my radiation pressure force, and thus control my mechanical oscillator. So these are sort of the two the two features that underlie most optomechanical experiments, measurement and control. To see how those come about a little more clearly, let me talk about how we mathematically model these systems. So starting with the cavity, if I have a factory pro cavity of some length L, that'll set the resonance frequency in terms of fitting some integer number of half wavelengths. Photons in the cavity can leak out through a number of channels, which are described by these loss rates, kappa L, kappa R, and kappa external, all of which make up the total cavity decay rate. And I will describe my cavity in terms of this variable A, the cavity field, and I'll drive it with some A in. And so to describe the evolution of the cavity, I can just use this equation here. So my cavity field is going to rotate at its cavity frequency, decay at a rate kappa, and I can drive it through one of the ports with my drive A in. So for the mechanical oscillator, I can just start with an oscillator of mass m, with a frequency omega m, dissipation rate gamma. And I could just work with Newton's law for this, but we usually choose to work with instead a complex variable c, which is essentially something like x plus ip. It's a complex phasor of motion, if you want. So this is some complex vector spinning around at a rate omega m. So this thing rotates at omega m, decays at rate gamma, and can be driven by some force. And the only difference between these two lines is algebra and an assumption that the quality factor of my oscillator, meaning the quality factor is very high, meaning the dissipation is very low. And so this Q factor is something I'll refer to throughout the talk. So now to put these two systems together, if I introduce additionally this optomechanical coupling rate G naught, these were my equations before. Now in the presence of this coupling, what I find is a position-dependent frequency shift and a intensity-dependent force on the mechanical motion. And so these are the coupled equations that describe an optomechanical system. Right now they are nonlinear coupled equations through this, but this nonlinear coupling is very small, and so the usual procedure is to linearize this system. We do that because we're assuming we're driving the cavity with some large coherent state, and so we're just going to analyze the system in terms of fluctuations around that large coherent state. So I'll assume that my cavity field is given by some large amplitude, A bar, plus these little fluctuations. And once I work through some algebra, what this gives me is that my effective coupling rate is enhanced by that factor A bar. So now I have a much bigger coupling strength alpha. If I make a few more assumptions like weak coupling and a high Q, I get this new set of equations for, now these are the optical fluctuations, and this is the same mechanical amplitude. So now this is just a set of coupled linear differential equations, which forms the basis for sort of linear optomechanics. So to say just a little bit more about this model and make clear this idea of measurement and control, how it comes out of this interaction, let me look at these in the Fourier domain. So if I just Fourier transform these equations, plug one into the other, I find that the optical spectrum is proportional to the mechanical motion, just scaled up by some coupling rate and filtered by the cavity transfer function. And so this is the sense in which by monitoring the optics, I can monitor my mechanical motion. So if I drive my cavity, I get these two scattered sidebands that encode the motion. At the same time, if I look at the mechanical spectrum, I find that it is given also by some response function times whatever the input is. And the response function almost looks like a regular mechanical oscillator, except that there's this additional sigma term here. So this is what's usually called the self-energy. This is just some term that is sort of modifying the effective mechanical resonance. So looking at how this appears, the real part of sigma is going to appear as a frequency shift. So that shifts my mechanical oscillator by the real part of sigma. And the imaginary part of sigma will change the line width. It'll dampen or broaden the peak. So this complex number, the self-energy here, depends on my laser power and my laser detuning. So by changing the power...
It can also narrow, right?
Yeah, it can broaden or narrow. So depending on my power and detuning, I can choose, I can control this optical spring and optical damping. And so that's all we're really going to exploit later on in the talk, is this ability to change the resonance parameters of a harmonic oscillator. Okay, so this is sort of all the optomechanics we're going to need. The system we're going to use is not a mirror on a pendulum, though. We use a membrane in the middle system. So the idea here is that I take my Fabry-Perot cavity with its standing wave, and I insert a thin dielectric slab somewhere in the standing wave, sub-wavelength thick. And the idea is that if this dielectric were at a node of the field, it would not perturb the cavity at all. But as I move it towards an antinode of the field of high intensity, the cavity sees in a longer path length, and it pushes the cavity frequency down effectively. And for certain regions, I get this nice linear relationship between cavity frequency and position. And so this is the same coupling I had on the last slide. This is what gives us standard optomechanics. So to implement these, we use silicon nitride membranes, which were introduced in Jack's group about 10 years ago. They're great for a number of reasons. One being they have low optical absorption, so you can send a lot of power through them without heating them significantly. They have large mechanical Q factors, so they have very low loss. We see 10 to the 7, has even been pushed up a couple of orders higher lately. And these have been and are being used across optomechanics for a lot of goals. These were the systems that have first demonstrated strong optomechanical squeezing and observing radiation pressure shot noise. And they're some of the largest objects that have been cooled to their quantum ground state. So this is the sort of system that we started building when I joined the lab. The result of that construction project was this. So starting on the left here, we see a black silicon chip with a 1 millimeter silicon nitride membrane in the center. It's sitting on a stack of materials for thermal anchoring and piezo for translation, and some thermal wires. We insert this into an optical cavity, which is around 3.5 centimeters long, with highly reflective mirrors on both ends. And we place the whole thing into our cryostat. The view inside the cryostat is sort of complex, but I just want to point out a few features. So part of the reason it's complex is that we have this all in a vacuum chamber and we dunk it in a helium-4 bath, and we need to couple light into the cavities. So we send light in on a fiber. The fiber comes down through the vacuum chamber, comes out here into a series of lenses to collimate the beam, and now we need to steer the beam into the cavity. So there's this series of cryogenic piezo motors for aligning the beam to the cavity mode. So we can steer this mirror and steer this lens. And so then we have the cavity and the membrane, and this whole apparatus is hanging on springs inside the vacuum can with copper fins and magnets for eddy current damping. So this is for vibration isolation within the cryostat. The cryostat itself is also sitting on pneumatic air legs for external vibration isolation. In the picture here, you can also see a large number of thin gold-coated copper wires for thermal anchoring. And for reference, this gold chamber here is the sort of the business end of the cryostat. Everything else is what we built around this to hold the membrane in the cavity. So a few more numbers about this system, some of which I've already mentioned. So the cavity has a line width of around 200 kilohertz. That should be 2 × 10⁴, not 10⁻⁴. So we use a commercially available membrane from Nocata, so we buy them for $20. They send them to us, and we get these queues of 1 to 20 million. It's a 1 millimeter square, 50 nanometers thick. Fundamental modes are around 300 kilohertz. And this, in the cryostat, there's sort of thermal occupation numbers around 10 to the 4. As far as our coupling, our G0 is around 1 or 2 hertz. For anyone that's familiar with optomechanical cooperativity, our bare cooperativity is 10 to the -4, but we can put something like 10 to the 8 photons inside the cavity and boost that up to 10 to the 4. I just mentioned this because the fact that our loaded cooperativity is 10 to the 4 and our bath occupation is 10 to the 4, this is what has allowed us in the past to actually access quantum effects with this system. So after a few initial cool downs, we eventually cooled down in 2013 and have been cold ever since. So this has been continuously dipped in helium because it's just proved to be a fairly stable system for exploring a lot of different physics. All those projects have used approximately the same optical scheme to interrogate this. So I just want to talk about sort of how we talk to the system. So we tend to use a scheme where we use 2 different cavity modes, one for measurement and one for control. So looking at this cavity mode first, here we lock the beam on resonance. This is our measurement beam. We lock it with some pound per Hall sidebands, and we put a local oscillator 80 megahertz away for doing heterodyne detection. So this is where this beam will acquire mechanical sidebands, which we'll read out by beating them off of the LO, and this is how we'll measure our motion. If we want to control our motion, we'll use this cavity mode down here. So this beam we lock with some arbitrary detuning, some arbitrary power, and this is how we exert our dynamical back action. So this is how we create optimal spring and damping or change the mechanical resonance parameters that is using this beam. To create these tones, we start with two physically distinct Nd:YAG lasers at 1064 nanometers. We pass them both through narrow line width filter cavities to strip away phase noise. We use a couple of modulators to create these different tones you see. We combine all the lasers, send them through another modulator for locking purposes. Send everything down to cryostat and look in reflection, and we split up that signal to generate our error signal and measure the motion with our lock-in detector. So with this setup, we've explored a number of things over the years. One of our early projects was looking at what happens when you have multiple optical modes coupled to one mechanical mode. Specifically, when you have optical modes that cross each other or have an avoided crossing, you can get a quadratic optomechanical coupling instead of a linear coupling. After that, one of our major efforts was trying to cool this millimeter-sized object to its vibrational ground state, which had a number of technical challenges, but we were eventually able to cool so that its average occupation number was below 1, and we were able to see an asymmetry in those two scattered sidebands, which you only see if you have a mechanical oscillator in its ground state and you're measuring it with a laser that is limited just by quantum noise. And then since then, we've really moved to this sort of mechanical multi-mode physics, including basically what happens when you couple two mechanical modes through an optical mode. And that's what has led us to exceptional points, which is what I'll talk about for the rest of the talk. So, moving into the second chart. So exceptional points. So before getting into degeneracies in open systems with loss and gain, let me just start by reviewing a few ideas about degeneracies in closed systems. So if I just consider a two-level system with some frequency splitting delta and some real coupling G, and this, I said two-level system, this could just be two coupled classical oscillators as well. There's it's mathematically equivalent to describe these two. And so I can ask first maybe what the eigenvalues of this system are. For example, if I can tune delta, if I have control of delta, these eigenvalues trace out this avoided crossing as delta is varied through 0. And this is sort of the picture one often has in mind when learning about the adiabatic theorem, where if I prepare my system in one of these branches and then slowly vary delta, my state remains in that eigenmode throughout the perturbation as long as I do it slowly enough. A little more exactly what that means is that if little psi sub n are my instantaneous eigenmodes, and I prepare my state capital psi in one of them at time 0, then my state's time evolution is just given by the eigenmode time evolution plus some phase factor, as long as I do things slowly. It can be interesting with this in mind to consider what happens if I can control not just delta but also G. So if I control delta and G, and I ask what these eigenvalues do, I get this set of intersecting tones with a degeneracy at the center. And now it can be interesting to apply the adiabatic theorem to perturbations of G and delta that go in a circle around the degeneracy and come back to where they started. Because as it turns out, the phase that you get in this case, the phase that I accumulate along this closed path includes two components. There's a dynamical phase factor, which just comes from accumulating phase from my frequency. And then there's this geometric phase factor, which it doesn't depend on how slowly or quickly I go around my loop. It just depends on the geometry of my loop and whether it encloses this degeneracy. And so this idea that there can be sort of interesting effects coming out of adiabatic circuits going around degeneracies, this is what I now want to extend to open systems. So what do I mean by open system? I mean something that's coupled to the environment. So it has, it's subject to loss or gain. And so that means to describe that, I'll use complex eigenvalues now. So I have a real part corresponding to a frequency, and an imaginary part that gives me a real exponential, so either loss or gain. So let me just take the toy model from the last slide and give some gain to one mode and some loss to the other mode. I'll say that it doesn't actually matter the size of this gain and loss. It doesn't qualitatively change anything about the results. And it also doesn't matter that I'm giving one gain and the other loss. I could give them both loss, but if I sort of take away the average decay rate or remove the trace of the matrix, I'll be left with something like this, where I just have a relative gain and relative loss. So I can so easily calculate the eigenvalues and ask, well, okay, how do they depend on delta? Previously we had the avoided crossing. Here, if I choose some value of g and plot the eigenvalues, now I have to split it into the real and imaginary parts. But here I still see that my frequencies have an avoided crossing, and my imaginary parts seem to cross. But if I'd chosen some other value of g, like 1/2, I would have found that my frequencies crossing and my imaginary parts not crossing. So something seems to be different. Let's just go ahead and jump to the 3D pictures. So before we had these cones when I considered the eigenvalues as a function of g and delta. In this case, instead what we get are these sheets, which are sort of, might be reminiscent of the Riemann sheets of the complex square root function. And they still have a degeneracy at the center, just like the cones did. But the interesting thing is that around that degeneracy, there's sort of this interesting topology now, where sort of smooth evolution in a circle around that point seems to move from one mode to the other. And so this idea that of sort of exchanging eigenmodes by this closed loop is what has drawn a lot of interest to these systems over the years. Because it seems to have some implications about, well, if I execute an adiabatic process that moves along these sheets, I can switch modes just by this closed loop. And so that's what we'll try to explore now experimentally. These were theoretically first really explored in depth in the early 90s. And then the first experimental demonstration came around 2001. And there have been a number of similar experiments since then, all generally accomplishing basically spectroscopy. So people would measure their eigenvalues. They can measure these frequencies and the decay rates and do it for different values of their parameters and trace out these sheets and confirm that they had the sort of topology that you expect. But in most of these situations, changing those parameters was a very physical process. So in this first paper, with a metal microwave cavity, and you had to disassemble the cavity and move one of the walls, and then put it back together, and then measure the frequencies again, and then eventually you could trace out these curves. But you couldn't do anything sort of smoothly and dynamically to actually see some adiabatic process where you put energy into the system and you vary the parameters smoothly and see that energy move. And this, it turns out, is a place where optical mechanics sort of works well because we have very easy access to tunable coupled resonances. So the resonances we can use are a pair of mechanical resonances. So for example, our membrane supports lots of different vibrational modes. For example, counting the number of nodes here, this would be the 1-3 mode, and I might call this the 3-1 mode. Because it's a nearly square membrane, these are nearly degenerate frequencies. So they're around 78 kilohertz in our case, split by about 500 hertz. And so the idea is that by applying our optical control, we can make these become degenerate. We can make them start to overlap. To model this, we can just take our the sort of linearized equation of motion we had in the first section and just add another equation of motion for the second mode. These two mechanical modes are not coupled to each other directly, but they do both couple to this one common optical mode. And so that's what allows us to generate the coupling. You can sort of solve this system using the same approach as before, work through the same linearization. And if I just write the equations of motion for the mechanical modes now, so if I write C1 and C2 as this vector C, their time evolution can be given by both this sort of intrinsic mechanical these intrinsic mechanical resonance parameters here, and also there's this coupling matrix now. So this is essentially the same self-energy from the first part of the talk, but now it's a matrix. It's a complex matrix that depends on power and detuning instead of just a complex number.
Can I ask you, is that a picture without optical control?
Yeah.
So you can measure it with there's a measurement thing. This is the unperturbed resonance.
Yeah, there's some small perturbation from the measurement beam, but these are largely the bare mechanical resonances.
They're accidentally non-degenerate because of imperfections in that particular number.
Yeah. We don't intentionally make it rectangular, but this corresponds to.
You guys don't make it at all. Right?
Yeah, exactly. That's
It's
right.
okay. Buy it if you can.
Yeah.
One other thing, how did you know that this is the 1, 3, and 3, 1? Did you measure a whole bunch of resonances?
So you can, if you sort of look through until you find the first nice large signal, that's your fundamental mode, and then you can pretty well predict from what you would predict for a square plate these vibrational modes, and they show up right where you expect them to. So we have these two modes. It seems like we should be able to couple of them. This is sort of the right ingredients for an exceptional point. So let's just calculate the eigenvalues of this matrix as a function of these two control parameters. That's basically what we did in the toy model. So if I do that and plot the real parts and the imaginary parts, so the real parts are the frequencies, and these are the, I'm going to frequently call the imaginary parts the line width, meaning the decay rate of these oscillators. And I find these sheets which are sort of distorted from what we saw in the toy model, but topologically they're the same, and they have this degeneracy at the center, and it has this property that going in a loop around them comes back to the other mode. So this is an exceptional point, so we should have one in our system. So the first thing we would do is to try to measure this. So all I need to do to see this is I take my control beam, I vary its power and detuning over a grid, and at each point I use my measurement beam, measure those mechanical peaks, fit their line width and their frequency, and keep track of this all. And when I put it together, we get these sheets, which match pretty well. We've got this degeneracy at the center and the appropriate topology around that point. So this means not only should we have an EP, we do have one, we can access it experimentally.
So, so you did probe the exceptional point experimentally. You didn't just insert them.
We sort of measured eigenvalues in the vicinity of it. We didn't get arbitrarily close to it, but
okay, that was my question. I mean, one aspect of this presumably is if you make a big loop, then even because of the topological property, you don't really have to narrow down where the exceptional point is to get the transfer effects that you're looking at, right?
Yeah, that's true. There are some limits on how big you can make the loop. Exceptional points always appear in pairs, and so if you make your loop blindly too big, you might accidentally enclose two, which is as good as enclosing none. The other EP? Yeah. So you notice these are around negative. This is around minus omega m detuning. The other EP appears at plus omega m, so that's a sort of a detuning range we never go into anyway.
So this is not a statement I'm familiar with, that exceptional points always occur in pairs. And maybe that's this 2x2 model. That's probably this 2x2 model. Because I know that, for example, there's an exceptional point in PT symmetric scattering, and there's just two eigenvalues of the S matrix meeting and leaving the inner circle. So let's see where the other pair is.
So I mean, here, for example, in the toy model, if I were to plug in a plus delta or a minus delta, I would find the same eigenvalues. I think in a 2x2, in a two-mode system, there have to always be two. I'm not.
You get control about negative frequency. Yeah, the frequency detuning. Negative frequency detuning, there's the other.
There's a meaning.
Yeah, negative frequency tuning. We
Yeah.
usually don't think of negative frequency if you are not working along the central frequency.
Yeah, I think you have to, I saw that statement in the thesis and I made a little mark because, I mean, we've been looking at lots of exceptional points and, yeah, that didn't seem to me like a general theorem about non-Hermitian systems. Maybe it's a property of these 2x2 models.
Something I can check out. So we have the sort of eigenvalue topology established here. I said we were going to now try to do this sort of dynamical experiment where we actually do some adiabatic process. So as a reminder, the idea here is that if I were to initialize my system into one of the modes, for example, the higher frequency mode, and then slowly vary the control beam in a closed loop, coming back to where it started, I would find that the energy in my system had smoothly followed the eigenmodes and it ended at the other mode, ended in the lower frequency mode. So this is also straightforward. I'll just take my measurement beam, record the energy as a function of time. This is sort of starting just some residual background energy, but then I'll drive one of the modes up to some large amplitude. So I'm essentially initializing the system into the red mode. Now I will turn off the drive, vary the control beam in this loop, and afterwards look to see where the energy is, and I find that it has been moved to the blue mode. It's switched eigenmodes, and then it just decays to 0. So qualitatively, this is what we wanted to see. If we want to talk about this quantitatively, let me define something I'll call the transfer efficiency. Just the ratio of how much energy is in the target mode, so the second mode, out of how much energy total is left. And so with this, we can now ask if this energy transfer behaves as we expect it to in different ways. For example, based on this sort of topology here, a large loop should transfer energy, and it does. And a small loop that does not enclose the EP should not transfer energy, and it doesn't. And we can do this systematically if, for example, we start with small loops and then gradually stretch them along the detuning axis until it encloses the EP. And we find that as we do that, as we stretch the sort of the side of the loop, we go from not transferring energy to transferring energy. And the black line here is the result of just numerically calculating the differential equation to predict the energy transfer, and it seems to agree well with what we found. Of course, there's lots of ways to deform a loop. You could stretch it along the power axis as well and find the same sort of behavior. Now, everything I've described so far is sort of implicitly assumed adiabaticity. It's used the adiabatic prediction. And it turns out that this is not always valid. In some cases, you fundamentally don't have access to your sort of naive adiabatic prediction. To talk about why, let me move back to the toy model for a minute. So here, looking back at the toy model, the black line I'm showing here is not just a cartoon now. This is actually sort of a numerical simulation of what a state trajectory does as I vary the parameters in a loop, where I've chosen some time that is slow in the adiabatic limit. And so this at least seems like an example where the trajectory really does follow the eigenmodes. This black line follows these sheets nice and smoothly. And this was starting at the upper mode and going clockwise. I could try to just reverse this process and start at the bottom and go counterclockwise. And again, plotting the result of the simulation, I get a state that really does follow the sheets. But there's sort of something special about these two trajectories, which is that they lie almost, in this case, entirely on the orange sheet. And I didn't really mention the color code yet, but these sheets are always colored based on the which one has the positive imaginary part, so based on which one has gain and which one has loss. And so what this means is that these trajectories were ones which lived entirely in the gain mode. And it seems like the adiabatic prediction worked for these. But if we were to consider the other two possibilities, for example, starting at the top and going counterclockwise, that would follow the blue sheet. And if we actually simulate this, what we find is that it starts to follow the blue sheet, and then it jumps down, follows the orange sheet, and comes back to where it started. We do not switch eigenmodes now. And similarly, if I start at the bottom and try to follow the blue, I also get this jump. And if I increase my simulation time, if I try to be more slow and adiabatic, this behavior doesn't change. So there's something sort of fundamental happening here. It turns out it's because of the presence of this loss and gain. So normally in the adiabatic theorem, the idea is that your system is in some eigenmode. You vary the parameters slowly, and maybe your state projects into the other mode a little bit, but if you go more slowly, you can sort of suppress that leak. In this case, if my system is trying to follow the lossy mode and a little bit leaks into the gain mode, that leak will begin to grow exponentially because of the gain, and therefore eventually dominate the sort of the projection of the state, and my state effectively jumps to the gain mode. And so you can say, well, what if I try to go more slowly? I still suppress the leak, but then my leak has more time to grow. So it has more time in the gain mode, and so you essentially can't avoid this non-adiabatic behavior. So this sort of results in this asymmetry between these different trajectories based on your initial condition and your direction. So can we see this behavior in our system? Previously, I just showed you results that successfully transferred energy. So here, this is back in the experimental system now, where I'm driving the red mode. I'm doing a counterclockwise loop, and I'm varying the loop time. And so of course, when the loop is very short, this is a sudden diabatic perturbation, and there's no adiabatic process. But once my loop time is long enough, now I have this adiabatic transfer, I move along the sheets, and I transfer energy. And just as a reminder from the toy model, this corresponds to some path like this. Similarly, I said I can reverse the path, so change both the starting mode and the direction, and that should also work. And it does. If I drive a blue mode and go clockwise, I transfer energy in the long time limit. But for the other two options, if I start in the blue mode and go counterclockwise, or start in the red mode and go clockwise, in the toy model, these were trajectories like this. I find in the long time limit, I do not have energy transfer. So this is where the non-adiabatic jumps are preventing me from actually moving energy from one eigenmode to the other.
Just to clarify, so in the previous case where we showed the model for your system and the original data showing that you found the exceptional point, you were using, I think, like red and purple or something, and then orange and blue here for the theory model.
So
what colors are which?
Right. So anytime you see blue and orange sheets, those are this toy model.
Yeah.
The red and blue sheets were from the experimental system. And so
yes.
Looking at these sheets, here the red and blue that I was showing on the last slide correspond to whether I'm initializing in this mode or this mode.
Yeah. But don't you also know what the relative gain is for those two modes? Or can't you map them onto the orange and blue toy model or not? Or?
Yeah, so just like in the toy model, the coloring here is based on which one has the larger, which one has gain and which one has loss.
Okay, so is red the same as orange, or is red the same as blue? That's what I'm asking.
So I believe red is the same as orange. So this is, I would say that this, I'm initializing in the red mode, and the trajectory lies mostly on the red mode. And
so that's the gain mode,
yeah.
Which is orange.
So,
what explains the peaks that you see in loop time? What does that correspond to?
So the explanation in the middle here, so this is sort of a very non-adiabatic regime. This is sort of traditionally adiabatic regime. In the middle, there's some sort of additional dynamical effects just coming from the fact that, at least my sort of understanding is that you're turning on some coupling for some fixed amount of time. You can get population transfer that way as well, just from, from sort of a pi pulse sort of perspective. You turn on the coupling for a fixed amount of time, you turn it off, you transfer some energy. So maybe that's partially explaining what's happening here. It's not in the adiabatic regime completely, and so there's some other behavior happening. So just sort of, yeah.
So for the two the gain sheets, the more typical curves, if you keep increasing the loop time, will you eventually don't have enough time that the cavity won't decay away because of the Q, and then eventually the efficiency go down eventually?
Yeah, so definitely throughout all these processes, there's energy loss from all the modes. And so this energy transfer efficiency we've defined here is defined in the way that, so you can remember it's normalized by the energy after the control loop. So that means that maybe even if we lose most of the energy, we just look at however much of it is left, where is it located. So essentially this would never go to 0, it would just get very hard to measure. At some point, basically,
Can you tell us in the thesis, you know, how much of the energy is actually transferred, you know, initially versus lost? In other words, is it 10%, 50%, 70%?
There is a plot where you can, that sort of conveys this, and if you want to have a backup slide.
And I think you just go back a couple slides and see it.
Oh, yes, it's on sort of a case-by-case example, yeah. Is this what you mean? So, well, this...
Yeah. I see.
Both
and
of
that's
these
a
were-
log scale, so actually quite a bit is log.
Yeah, so this might not be one of the, if I go back one. I mean, so here's an example. This is a log scale as well, so maybe we lost half the energy here. And this might not have been if you really wanted to just see the most energy transferred, there might have been a better choice of time.
You didn't worry about that too much.
Right, we sort of,
I mean, if you were thinking about actually using this for some application,
yeah, exactly.
you would care a lot about, you know.
Right, and you might then, so part of the reason, so the reason you have this loss is that you're trying to adiabatically follow a sheet that has loss. And for example, if you make your loop bigger, that means you're traversing regions of higher loss in our system. And so you might find that if you really wanted to achieve actually efficient energy transfer, you would want to optimize your loop size somehow so that you enclose the EP, but you don't go to high loss too much. So one way that you might summarize this behavior would be to say that you could describe this operation as a propagator matrix that sends your initial state at time 0 to your final state at time t. And essentially what comes out of this is the idea that this propagator matrix is not transpose symmetric. So in the language of scattering matrices, we would say that this is a non-reciprocal matrix. So this sort of asymmetry based on initial condition and loop direction, that was sort of one of the last pieces of the puzzle that had been predicted about this adiabatic behavior and had not been demonstrated until this. So this was sort of the last thing we wanted to demonstrate in this experiment. Now I just want to mention that, so all of these results sort of started from a somewhat fortunate symmetry in our system. If you remember, I said we had this nearly square membrane, which gave us these nearly degenerate modes. They were only 500 hertz apart. That sort of is what allowed us to, because they were so close to begin with, our control beam was enough to bring these modes into degeneracy. We could make them overlap and couple to each other. If they had been 5 kilohertz apart, first we would have needed 10 times more power to reach the EP. We would have needed 10 times more optical power to make them overlap and make them couple. Also, the line width at the EP would have been 10 times larger, which means we would have had 10 times more loss during our circuits. So this was sort of fortunate in a way with this behavior was restricted to these nearly degenerate modes. So one question is, can we avoid this and do this with any pair of mechanical modes in our system? And the short answer is yes, and I'll talk about how that works now. So the idea is, suppose I drive my cavity with one laser here. It acquires some mechanical sidebands that are very far apart from each other. Maybe this is 400 kilohertz and this is 800 kilohertz. So they're too far apart for me to make them couple with just one beam. But if I drive the cavity with the second mode now, so I drive with this blue beam, and I choose its detuning appropriately, I can make its omega 2 sideband, omega B sideband overlap with the red laser's omega A sideband. So I'm making these peaks overlap, even though they wouldn't normally. And I can sort of throw away these off-resonant guides. They don't contribute to the analysis much. And I won't work through this, but let me just say that if you go through the same sort of linearization procedure as in the simple optomechanical system, if you work through with two drives, what you find is that there is a coupling between these mechanical modes now because you've made them overlap. So essentially, this mode's motion will drive this motion. This A will drive B, and B will drive A, and there's a coupling between them. This is sort of a mess, but let me just say that these are the final equations of motion for the A and B modes. And importantly, the A mode is coupled to the B mode. And normally they would live at different frequencies, but I have this B node between these lasers, which sort of makes this a resonant interaction. So not only do I have a coupling, if I look in an appropriate reference frame, these modes are effectively degenerate. If I look in the frame of the cavity, I can see that these sort of sidebands are degenerate. And so what we're going to do now is look for an EP in where we've shifted one of the modes to this other reference frame. So I now have two control beams. I have two powers and two detunings to work with. So I have sort of 4 parameters to choose from to look for an EP. Let me just say we choose some combination of these, something like a mean power and mean detuning. And so we vary these parameters and look at the frequencies and the line widths, where the frequencies are in this shifted reference frame. And we find some sheets that are, again, a bit more distorted, but if you check, they still have this degeneracy at the center, and the topology around them is still equivalent to the toy model. So this says we should have an EP in between these modes as well, or at least we call it a virtual EP because we're sort of in this other reference frame, and the modes themselves are still living at very different frequencies. So first thing would be to measure the eigenvalues like we did before. So let's just add a second control beam to our setup. This is easy to do. We drive our control beam AOM with 2 tones instead of 1. And then we vary the power and detuning and record these eigenvalues. And what we get for the frequencies are shown here, and the line widths are shown here. The line widths are sort of difficult to see, but here we see that these do have sort of the right shape. The gray mesh is the prediction based on the model. And we seem to have this degeneracy at the center and the appropriate topology. So again, it seems like not only should we have an EP, a virtual EP, but we can actually access it and measure it. So now, can we do the same dynamical energy transfer? The sort of short answer is yes. So this is sort of repeating the plots we saw from the previous experiment, sort of just an example showing transferring energy through some control loop where we vary both beams now. This is showing that we have the energy transfer depends on the geometry of the loop and matches our prediction, and it depends on the adiabaticity of the loop, and there's this asymmetry between red and blue and clockwise and counterclockwise. So in general, we can reproduce all the same results now, but without this restriction that we work with these fortunate mode pairs. So that's sort of the end of the story, is that we were able to extend our initial results to this sort of more broad class of multi-mode systems. So with that, I'll sort of wrap up, and just a few takeaway messages would be that dissipation is not always a boring thing in your system. It can give you some interesting effects. And even something as simple as coupled damped harmonic oscillators can give you fun things like non-trivial topological features. And then finally, this seemed like a fortunate parlor trick initially, but we were able to extend this. So I just want to thank the people I worked with. So I built the system and carried out the quadratic and ground state projects with Calvin Lee and Woody Underwood. The exceptional point physics has been done with Haitan Zhu and Liao Zhang. I'll work with Jack here. And with that, thank you for the attention.
Okay, thank you, Dave. So the usual approach is that use this time to take questions from non-committee members, and then afterwards we'll have just committee talk with Dave. So first question from the panel audience.
I want to keep harping on the second to last slide, where it shows the blue curve on the right there. It looks like it gets to the 100%.
Right. I think it's the same explanation as before. I would say I think the details of what happens in this regime depend on the sort of the shape of these sheets in relation to sort of the shape of your loop and how closely your loop is passing to the EP. So I would say this is a regime where it does depend on the details of your loop. Once you're out here, once you're in the very long time limit, at least for sort of these adiabatic trajectories, you can really say the local details of my loop don't matter. I just have to enclose the EP and I get this energy transfer. In the middle here, that's not true.
So if I understood correctly, exceptional points are a feature of any mechanical coupled oscillator system?
And any coupled oscillator system. So the other, most of the papers we find about this are in optics or photonics, where these are coupled waveguides or coupled cavities.
So supposing I was interested in realizing an exceptional point in an entirely mechanical system, let's say in junior lab or something, like a couple of pendulums, how would I be able to do that? What would I need to be able to do that?
So you would need them to be coupled pendulums, and you would need to be able to tune that coupling. So if you just want to measure, these sheets, in principle, you just need to be able to adjust the coupling and adjust maybe the frequency of one of the pendulums. To this sort of dynamical behavior, I think the advantage our system had that allowed us to make these sort of measurements where we put energy in the system and vary it in loop is that these were, we have a lot of precision in our measurement. We can measure the amplitude of these modes very precisely. So even if when we do this loop we lose energy, we can still measure that energy fairly well. So we have a good record of even if we lose half.
But the damping has to be especially small, or is there some guide to what parameters I need? I would need.
I don't think the damping needs to be particularly small just to create an exceptional point. Because our oscillators start with very small damping. They start very high Q, but the line width in these sheets that I show goes up to kilohertz or something. It goes to
still pretty low.
Yeah, it's a pretty good Q still, but worse than we start with.
So suppose that you started with two undamped oscillators with fixed coupling, and all you could do was tune their frequencies. So you want to draw what their frequencies would look like in that case?
You would mean,
yeah. So now suppose that I want to turn on the dissipation from 0 and start to increase it. What feature on the drawing you just made would I have to make the damping bigger than? Or comparable to?
You would need the damping to be, so if this is twice your coupling, you would need to be able to make the damping on the order of that. And I'm not sure that would necessarily be hard to do in a physical system.
I don't think it would be possible.
I mean, I think Carl Bender demonstrated PT symmetry with 3-foot pendulums at some point in a paper. And there is a paper just demonstrating this topology in RLC circuits, not superconducting fancy circuits, just dumb circuits.
Well, at least some of this was done at Wesleyan, so you might actually be able to just talk to the people at Wesleyan if you want to do it with electrons. Or maybe you'd rather do it. Wow. Oh, you're not actually going to do it. Okay.
Other questions?
If not, let's thank Dave again. You guys want to maybe meet at 5? Take a 5 minute break.
Sure.
Right here.